Hello and welcome to my talk at Scylla Summit 2021 on optimistic concurrency using right-time timestamps that are available in Scylla. My name is Dan Podhola. I'm a principal engineer at Zillow. I've been at Zillow for a bit over 8 years. You can see my slide, my resume, if you will. I will kind of just briefly go over that I mostly specialize in database performance and tuning, the backend services that talk to them, and I have kind of a wide range of experience in that realm, massively multiplayer online games, large batch processing, and most recently, real-time streaming ingestion. So what are we even doing? By we, I mean my team at Zillow. My team is responsible for processing property records, records about properties, and listing records like for sale, for rent, that type of thing, and mapping those to a common Zillow property ID, if you will, and translating different message types into a common interchange format so our teams can talk to each other using the same type of data, and also deciding like what's best for display. I have a quick little diagram that shows like a very high level version of what we do. So we receive a message, we translate it into a common output format. We fetch other data that we know about that property that's also in that same format. We bundle that data together. We choose a winner. I use the term winner lightly here. And we send that bundled data out to our consumers. So what's our problem? Why am I giving a talk at Scylla Summit? Well, our biggest problem is that we have a highly threaded application, and then we receive two different message queues from two different producers. As a result, the messages can be received out of order, just by the nature of the queues themselves. And our team cannot go backwards in time. If we were to go backwards in time, it would cause bad things to happen on the site and for analytics and all the other different systems that consume our data. So what's an example of that? An example of that would be we have a message that says this property has changed price. That message is a for sale listing. And we have a message that says this house has been sold. Now, if we were to process the message that says this house has been sold first, and then process the price change message, we would have a house that was for sale that had been sold, and that would remain that way until the house was relisted or some sort of manual intervention from maybe a consumer complaining. That's not a great experience for anybody, not a great experience for our analytics team. So here's a quick visual representation. I'm a visual person. This is what I need to learn. So you can see here that I have a message that comes in first. The message was generated at time 2. It goes all the way through the system. At that point, we publish it. It's golden. So that's actually what we want. We want to have that latest message on the site. However, we then, from a backfill queue or whatever, receive a message that was generated at time 1. It goes through the whole system, and when it's output, it is out of date and now overwriting the proper record. So what's the high-level solution? You may already be thinking, well, just don't write the older message. Well, that's a good solution, and I agree with you. So I drew a diagram here that shows a decision tree that I added in the middle. It says, if the message is newer than the previous message, then write it. Otherwise, don't. Just skip to the fetch. Now, you might be wondering, well, why fetch at all? Just stop there. If you were grabbing a transaction lock and doing this in like a SQL Server type of way, I agree that's a good solution. I drew this in the manner that we're solving it, and I'll explain this in a little bit. So how do we implement it? Well, traditionally, for me at least, the way I would do this is I would spin up a SQL Server instance. I would grab a lock, run a SERP procedure, and have that SERP procedure return like a result code. Like, was this written, was it not written, and then act on that information. Downsides here is that you have locking, and you don't have the scalability that comes with something like Scylla. We could also do like LWT in Scylla too, but we wanted to avoid that for performance reasons. So the second method is store everything. What does that mean? That means we get every record and we store it no matter when it was given to us, and then we have the application layer pull all the data at once. It does the filtering, and then does action on it. The problem with that is we have to trim data because we don't need all the data, and we just didn't want to have to deal with like running a trim job or like paying to store all that data. We just didn't need. Our system just needs to store the latest state, the most current state. And then finally, there's the overwrite only if newer, but without a lock method. And that's what I'm going to get to here in a second. The downside is if you don't know if your write has written to the database, like actually committed the write, then you have to republish the results every single time. And I'll get into that too. So this brings me to my using timestamp slide. Using timestamp allows you to replace the timestamp that Scylla uses to decide which record to write or not write, as it were. This is normally a great thing that you would want. You have a couple of nodes, 2 messages come in. Those messages have different timestamps. Only the latest one will kind of survive the consistency. The upside, however, you can use using timestamp to supply your own timestamp, and that's what we're doing here. And this allows us to pick a timestamp that we decide is the best arbiter for what is written and what is not. And the upside is that it solves our problem without having to use LWT or an application lock like using Redis or something. The downside is that we don't know if the record was actually written to the database. So the workaround for that is to pretend that the record always has written. Some additional details here. You have to, or at least we have to, ensure that we get the latest documents back when we ask for all the documents. So for us to do that, we have to write at quorum and we have to read at quorum for at least just these 2 statements. This allows us to avoid conditions where you might write just a single node and then you fetch, and that fetch could even be in quorum. If you don't write at quorum, you might get you pull it from the other 2 nodes and get an older result set, which would mean that we could flicker and send an old result that we don't want. So quorum here solves that problem. We didn't use all because if one of the nodes go down, we wouldn't be able to process at all. So here's a quick system overview just to see how our system works in general, to give you a little more context. This is my message flow diagram. You can see at the top there's a data service that has its own data set. It publishes to its own real-time, its own backfill queue. There's a more complicated service down at the bottom that mostly streams data in from Flink, but has a manual data retrieval service that allows people to correct issues or manually request individual messages or properties. And then there's a Flink state on the bottom that uses some magic to fill backfill queue. Another interesting thing here is that the listening processor, which is the service that my team has written, takes messages from those queues and actually publishes them differently. So it'll publish real-time messages to a Kinesis stream, and it'll publish backfill messages to an S3 bucket. We have some additional kind of required producer actions here. So we use some engineering to figure out, well, these different systems operate in different ways and might theoretically have older timestamps. Like, for example, a backfill would be a great example. You generate a message, it goes into your backfill bucket, and then you publish a real-time change. Well, if we happen to be processing the real-time change and then the backfill later, that message would have an older timestamp. Now, if they were produced at roughly the same time and their system had different ways internally of like how it generated that message, then the message generation time could be wrong. So we've required our producers to give us the timestamp in their messages that is the time that they fetch the data from their database, because their database is their arbiter of what's the most recent record that was in there that they send to us. This also solves our delete scenario. So if we were to manually delete a record from Scylla using one of Scylla's timestamps, in order for us to get a fresher message on the delete, we actually have to ask for a fresh message timestamp. So going to that service that requests individual messages, we would get a fresh timestamp that's newer than the one that Scylla has for its delete. So what's our performance like? Well, our performance is been great. Our normal real-time workloads, it's been ample. We run on 3 i3-4XLs for Scylla. Our service actually runs on a single C5XL. It has 25 threads. It auto-scales in EBS, so if we happen to have like a small spike in real time, we'll scale up to 3 C5 XLs, turn through that data, and we'll be done. The real beauty of this is even just on 3 nodes, we can scale up to 35 of the C5 Excel instances, and we'll process over 6,500 records a second, plus the real-time workload. So we won't even no one will even notice that we're processing, the entirety of Zillow's property and listings data, maybe to correct some data issue or change a business rule. The beauty of that is that we can process the entirety of the data at Zillow, that we care about at least, in less than a business day. And again, no performance hit to real-time data. So that's the conclusion of my talk. I hope you've at least found it interesting. You can reach me on LinkedIn if you have any questions after this presentation. If you're interested at all at working on big data or high throughput systems at Zillow, zillow.com/careers. Thank you for your time.